everybody. My name is Alyssa Emerson, and this is David Myers, Maha Shaw, and Nolan Beard, and we're here to present to you our project on the production planning and workflow improvement in the fiberglass department at S. Bravo Systems. This company manufactures secondary containment sumps, as you can see highlighted in orange, and they house fittings, and their main purpose is to prevent any oil from leaking into the ground and contaminating the ground water around it. In recent EPA regulations of 2018, these sumps are created mandatory, and so this company is planning for an increase in sales and also an expansion to move to Tennessee. Some of the issues that the company is having is that they have delayed shipments, there's a ton of waste everywhere, and customers are being turned away, and there's no proof of regulatory compliance. So our objectives for this project were to decrease the delayed shipments, to increase production capacity while eliminating waste, and also increasing the quality for our products.
For the scope of our project, the company asked us to assess their fiberglass department. To do this, we created a Pareto chart which limited us to the 3 molds shown on the right, which make up about 95% of the fiberglass sales. To present this project, we will be going through 2 phases. Phase 1 being our current state analysis. We will present the current process, the issues involved, and the tools we use to identify the root causes of these issues. And then we will go into phase 2, where we will present industrial and manufacturing engineering techniques we use to resolve these issues. Starting off phase 1, we'd like to talk about the current process. The current process consists of these 7 steps with the associated time shown underneath. The main things to notice here is that the cure time of 240 minutes. Although no worker is required to complete this task, it does put a crutch on our mold limitations. Also, the rolling time of 13 minutes is our longest process time that requires a worker, but there are 2 workers assigned to this task. The mold retrieval and mold re-rack could be considered a setup and breakdown time with proper scheduling. And the last thing to note is that the prepper, shown by the red, is in charge of 4 tasks and 4 moves. Following our time studies, we conducted a work sampling. The main things to notice from the work sampling is that the prepper utilization shown in red is higher than the other workers. Also, as the week goes by, our utilization goes up. The last thing to notice is that our average utilization is relatively low at 55%. Using our time studies, we created a simulation which resulted in a preparation worker bottleneck of 100% utilization. This is no surprise because of the 4 tasks and the 4 moves that were assigned to the prepper. When comparing this to our work sampling, where the prepper had a 65% utilization, this showed us that there's something starving our process from outside. We later identified this issue as scheduling, which Alyssa will now talk about.
Like Nolan said, after gathering the data samples, we decided to create this list of problems that we had in regards to scheduling. First, a lot of the engineering drawings and orders were being lost because it was a manual process. Second, any changes that were made after the order was already printed were not always caught because, again, a manual process. And lastly, the workers didn't really know which molds to use because there's no nomenclature to distinguish which part goes to what mold. So we decided to look at the flow of the orders through the fiberglass department and how they all started. So first, orders are called into the company by customer service and they're entered into QuickBooks. Once they're entered into QuickBooks, multiple copies of that order are walked down to the production line and given to them. This causes the issues that I highlighted in blue. This is just a few of those issues. And just within the first few months of 2018, there was over $300,000 worth of cost for delayed shipments, and over $150,000 was due to our fiberglass department.
This is our current facility layout of S. Bravo Systems in Commerce, California. We were asked specifically to focus on the fiberglass department, which I've highlighted in red. So we're going to zoom in and show you how this process works. You first start by picking and retrieving a mold. You then take it to be prepped. Then it's taken to be chopped, and this is where the fiberglass is sprayed on. It's then rolled, cured, demolded, and then taken out of the system. We had observed distances with each of these processes, and we had noticed that the worker is actually doubling their distances. So initially, they should be walking about 270 feet, but it ends up being 540 feet where it's doubled. and this shows our inefficient layout of their current state. So the main issues that we noticed when we looked at the layout was that there's molds unorganized, they're unlabeled, and they're spread through the center of the facility. They're really difficult to find because they're just scattered all around the floor. And lastly, there's unnecessary movement.
To begin our discussion of the issues of quality at Bravo, I'd like to begin by looking at the three main requirements that stem from the EPA regulation highlighted in red. The first is that sumps need to be capable of detecting and collecting releases. Secondly, they need to be constructed with sufficient strength and thickness to prevent failure when they're installed. And finally, they need to be able to detect their own failure. Bravo guarantees that their products meet these regulations and provides a 1 year limited warranty on factory defects and a 30-year limited warranty on corrosion of their fiberglass. To determine whether or not their products actually live up to these standards, we examined the manufacturing process, illustrated in this diagram, to determine what defects are most likely to occur, how they are detected, and how they might be prevented in the future. In the coming slides, we're going to be looking at cross-sections of the sump wall like the one shown here. The first type of defect is that of uneven thickness. This can lead to a weak wall that fails once it's installed. Uneven glass density. This can lead to a pattern of cracking, which leads to leaks after it's installed. And finally, an incomplete roll-in, which leads to delamination of the sump wall later in its life. These three types of defects all take place before the curing process. And as you can see from this table, they're relatively simple and easy to check for and repair if they're caught. Unfortunately, it's up to the personnel on the line to catch these defects and repair them. And because there's little oversight and no traceability, complacency can set in. We can see strings of defects. This fourth type of defect is that of blistering. This is due to an improper ratio of catalyst to resin, and this can affect up to 3 or 4 hours of production before the error is caught. Finally, air bubbles suspended in the resin are the most common type of defect, and both of these types of defects take place after the curing process, and so they take much longer to fix and therefore are more costly. Typically, this is where I present data about the number of units inspected, the defect and scrap rate of the warranty claims that have been submitted. Unfortunately, Bravo does not collect any of that information at present. This is because they do not have a permanent traceability solution in place. Instead, workers are responsible for catching and repairing defects as they occur. We'll get a little bit more into that later, but the bottom line is that Bravo can't demonstrate that their process is in control, nor can they really assess the state of their quality.
So this summarizes our current state analysis. The issues that we found in phase 1 were that we have a lot of delayed shipments in the company, demand exceeds capacity, there's wasted resources, and regulatory non-compliance. With analyzing these issues, we've completed our current state analysis. Then we move on to phase 2, which is our future state analysis, and we're going to talk about how we're going to address each of the issues that we found. The first are in red, which we will address by improving production planning and scheduling. The next are in blue, which we will be addressing by facility redesign. The third ones are in gold, which we will be addressing by introduction to measurement of quality. And lastly, the issues in green, which we will be addressing by line balancing through simulation. I'd like to now transition back into facility redesign and how we will be addressing the issues in blue and how we observe them in our future state analysis. So we received a layout of our future state analysis, and I would like to point out that this facility layout is different than the current state analysis. This is due to the fact that the company is moving their entire operation to Tennessee. So we were given this layout, and we were able to come up with 2 alternatives of what we think is best to have them create for their fiberglass department in Tennessee. Here's our alternative 1. The main changes I would like to point out is that we have more space available for the molds. This is due to the fact that we were going to be adding more storage racks so that in the current state, the molds that are all over the floor and disorganized will be put in a certain spot. In addition, we will be implementing a heated curing room, which I'll get into in a couple of slides. And lastly, we were able to eliminate this large gap, which is a waste of space, and it causes a waste of time for grabbing the molds and moving between processes. Transitioning to alternative 2, the main things to notice here is the allocation of space of each department and the proximity of each department. In addition, we also eliminated the gap in this alternative. As I stated, we plan on implementing a heated curing room in either of the alternatives we choose from. So currently, the Commerce facility has a heat exchanger, and this is used to get rid of any chemicals that are made during the process. We plan on shipping this heat exchanger to the new Tennessee facility and harvesting that excess heat to create a temperature-controlled room. In addition, we'd like to implement high-speed doors so that there's quick access in and out of the heating room and the temperature does not change. With the investment of about $7,500, we cut our curing time into half, which David will get into in a couple of slides. And lastly, which alternative did we choose for our facility redesign and why? Alternative 1, due to the fact that we maximize usage of space and we have less distances between the departments, which will be more useful and reduces waste.
In order to address the issues that caused the delayed shipments, we decided to use a high-level approach. So what we did is we redesigned the flow of the process of the orders going through the department by automating some of their processes. So you can see here that we decided to use a software that we call BravoNet, and it gives access to all of the leads to see any changes that are being made throughout the day at any time. We also recommended that the company have 30-minute production meetings in the morning just to get their day started. And this is a quick view of what it looks like in the software when a lead logs in to see what's going on. And what we did is we created an algorithm to prioritize. It's not the most optimal, but it's much better than what they have currently. So the program, it filters based off of 3 things. First, the number of products that are needed in the order. Second, the shipping date. And then third, the availability of the molds that we have. In order to create this algorithm and to automate it, we needed to create some type of nomenclature for the company. So we created an entire nomenclature system for the molds, and now each mold is associated with every part in the company. So here, A2 is a mold association code for this particular UDC sub, and all of our employees are trained in it now. With these changes just in scheduling, we have seen about an 87% reduction in the cost of the delayed shipments.
I'd like to return now to the discussion of the quality issues at Bravo and how the introduction of traceability and control can address the lax work standards, instill a sense of responsibility in the individuals on the line, as well as address the material issues that are leading to our most serious defects. The first of those defects is that incorrect catalyst ratio. If you'll note in this table on the left, in the first column, the combination of temperature and catalyst ratio affects the cure time as well as the quality. At present, workers on the line are responsible for leaving their workstation and manually adjusting the catalyst ratio using the mechanism shown here. When this is forgotten or done improperly, it can lead to that string of errors that I talked about earlier, 3 to 4 hours of production damaged. To mitigate these issues, we're going to be holding the temperature constant at 95 degrees, which eliminates the need to adjust the catalyst ratio throughout the day and throughout the week. This eliminates a lot of the defects that we're seeing from this blistering. The second quality issue that we're looking at is lack of traceability. As I mentioned, right now, personnel on the line do not feel accountable for their product's quality, and Bravo can't assess the state of quality in their processes. This is because they lack traceability in their process. Although temporary part marking is used when a string of defects occurs, Bravo's never implemented a permanent solution because external labels are ruined by follow-on processes, and internal labels, like the one shown here, are obviously difficult to read and impossible to scan through the resin layer. To overcome these challenges, we propose using UV light activated labels like the one shown here. The advantage to this is that scanning is unaffected by the resin layer, and so we can embed discrete part information with every single product. These labels would be automatically generated by the scheduling software that Alyssa mentioned, and would be printed from each station where the work is done. This would allow Bravo to quickly trace defects back to their source, as well as collect the information they're going to need to make better quality decisions in the future. Implementing this solution is going to cost $6,500 up front, as well as add 11 cents per part in materials cost.
To combat the issues of workers being unproductive and the bad task grouping, we turn to line balancing. Before we jump straight into line balancing, I'd like to talk about the recommendations that have been made that improve the processing time. These have all been previously mentioned except for the two-handed rollers. We recommend two-handed rollers because it will reduce the amount of time it takes to roll and improve the working conditions. Circled here in red shows how these recommendations change with processing times. The mold retrieval, rolling, curing, and the move times have all been reduced, bringing our total time from 284 to 150, about half. Now that we've taken into consideration the changes in the processing time, we'd like to turn to line balancing. In alternative one, we'll still have the same 4 workers, but the task will be reallocated to the chopper is now in charge of picking up the prep mold from the prep area, and the rollers are now in charge of taking the cured product from the cure room to the demolding and demolding it. In alternative 2, we will keep the same task assignments of the current process, but we will be adding an extra prepper. Using these 2 alternatives, we ran simulations, and based off these simulations, we recommend picking alternative 1. This is because of the lower cost per part at $6.94 and the higher average work utilization of 89.2%.
In conclusion, we recommend the following. We would like to implement the heat curing room in addition to continue using the labeled molds in storage areas. I would also like to use the proposed alternative 1, as you can see here. We would also like to implement the traceability using the UV labels, as well as continue to use BravoNet, which is the scheduling software. Lastly, we would like to use the line balancing alternative 1, as you can see here, with 4 workers. And with these recommendations, we have an initial investment of about $20,000, and we plan to save the company $65,000 a year approximately over the course of 5 years just within this department, bringing our net present value to $231,000. We'd like to thank Dr. Falafini for being our advisor, the IME department, and then Fausto Corona at SBravo. Any questions?
All of you guys are nice, but David is usually the nicest. And he asks a lot of questions, so
It's
have
true.
all of us.
I'm ready for you.
Okay. You know, something at the very beginning, it was very difficult for me to follow the whole thing because you weren't telling me from the beginning what you're supposed to be doing. So kind of, remember we talked about the elevator talk and all of that. Have some kind of a thing at like 1 minute that this is what I'm doing and this is what's going to happen, so I can follow it much better, just because of the fact that you guys did so many different things. And the transition wasn't good. You know, you stopped talking, Elisa started talking, and I had no idea why you were going back and forth. So kind of like if you have a transition going to Elisa, like she's going to be talking about this and why. Can you go to the current state's pictures?
Sorry.
And that slide that you have for go back, the one that you have 3 or 4 of them at the same time.
Oh, David's
David
quality.
was talking about.
What's the topic we're looking for? I'm sorry.
The current, go back to the current state, the quality issues. You have like 3 different
Yes,
types
sir.
of quality defects. Yes, great. Okay. So you talk about these pictures.
Yes, sir.
Those are, you didn't talk anything about the right-hand side. Why are they there?
What I'm trying to show on the table on the left, and I'll do a better highlighting in the future, is that the time to catch and then to repair the defects that I talked about on the left-hand side of the slide is relatively
But
short.
now you're trying to tell me what the defects are. So concentrate on the defects so I know what they are. And maybe 1 picture at a time so I can see it better. You see what I'm saying?
Yes, sir.
And then you talk about the improvements.
Okay.
And for quality issues, did you use design of experiments?
We saw the opportunity to use that, especially when it came down to the balance of time, catalyst ratio. A design of experiment had already been conducted by a previous group, and then when we really looked at it, we realized we could address the root cause, which is that fluctuation of ambient temperature, and it alleviates the need to do a design of experiments. But it is a thing that we'd like to do in the
So
future.
it would be nice to show it
Okay.
as a part of this project. And the line balancing graph. Can you go to the line balancing graph?
The one in the future.
The one that no one is. That wasn't showing me line balancing anyway. The picture, the graph wasn't showing me. When you're talking about line balancing, what you do.
I should probably do a better job presenting it, but the colors represent the workers. So I have 1 prepper, which is the red, the chopper, which is the blue, and the rollers, which is the green.
So are you telling me that the prepper does the first and the second element and then waits
it kind of comes in a full circle. So he's not moving all the way at the end of the line.
This graph is a success story.
You want to,
And the cost savings, at the end, all of a sudden you come up with 65,000 a year.
Yes.
How'd you end up with that?
We added the cost savings that we.
I didn't see it.
Oh,
okay.
sorry.
No, at the end you
It's like
said.
he wants
Oh,
to
so
see
you want
how
us
we-
to list it?
Yeah,
Like
how,
how-
Okay.
where does it come from all of a sudden?
Okay.
Got it.
Thank you.
for that feedback.
Same questions, like, before you had a door there, shows the approximate.
Yeah, approximate cost.
It's really
Go
here.
to that.
You have to go back
Go to
to.
the approximate.
Oh, all the way?
It should be an even number. I realized that after you mentioned it.
Especially because you had approximate cost.
Approximately 90 minutes.
That one penny,
Right?
really important. Yeah, we'll make sure to change that.
Approximately down to this end.
Everybody. Make sure you pay attention.
I have a couple of things. So one is, you had the defects, but you never addressed how they were fixed, or if they were fixed, or if they're just going on.
I'm sorry that I didn't tie that together better. I was trying to point out that the lack of accountability would be solved by the fixability solution, as well as the sharing, but I'll do a better job of saying that.
Okay. The other thing, you had a slide that indicated that they are running about 6 parts per hour, and I think the cost was about $6 per piece or something like that.
Yeah.
I think you passed it,
Yeah, I did.
right there, 42, 41.
This one?
No, but there was one, cost per part. So here you have, like, for instance, the alternative one, you have 7 parts per hour, $7 a piece. Are you telling me that you're spending $49 an hour?
No, this is the cost per part. So,
So
yeah,
So the
yeah.
entire cost in 1 hour is, $40-something.
in labor. This is labor cost per part in labor, I didn't, sorry.
For 4 people?
Yeah.
By that number, but okay. Seems very low.
See your math. I see your math, I understand. Yeah,
So-
I'll look into that.
And the other thing that also is not clear is that this is only labor cost. So I wasn't sure if it included materials and those types of things.
Okay, yeah.
Thank you.
Okay, thank you.